All right, let's start. Do you have any questions? All right. So we're done with 4.2 from last time. So let's review what the main points are for 4.2 and 4.1. So the first thing, right, is we look at how to model a process as a Markov chain. Okay. And here, how to model a process as a Markov chain involves the following considerations. So I guess the biggest thing, right, is how to define a state. Because I think so how to define a state or the state space, right? Which is the collection of all states. Because that's probably the biggest thing you have to consider when you try to model a Markov chain. So for example, right, what examples come to mind? The first example is the one with the weather, right? 2 consecutive days weather. Which influence the next day, right? So for example, rain, rain becomes rain, rain, not rain becomes not rain, whatever, right? That kind of thing. So here you need to like let the state, right, be the weather in 2 consecutive days. So basically you cannot, right, model the weather day by day, for example. Okay. So that's one example where you have to define the state carefully. Another example would be the one where you try to track the pattern, right, of a Markov chain. All right. So the broadest example, right, we look at is the first time, right? So X is a Markov chain with states, let's say 0, 1, 2, 3, right? And you want to find the first time the pattern 1, 2, 1, 2 happens. And so to do this, right, you need to design YT, right, a Markov chain that somehow can track, right, this pattern. And we explained last time how, well, so first of all, right, you don't want to track everything. In other words, you don't want to track all 4 states, right? So on the other hand, though, right, so on the other hand, if you just use 5 states, that's not going to be enough. For example, right, where 0 means no pattern, 1 means, right, starting with the first one, right? So 0 tilde means no pattern. 1 tilde means you have a 1, right? And then whatever comes before that, right? 2 tilde means you have 1, 2. 3 tilde means you have 1, 2, 1. And 4 tilde means you have the pattern, right? And here, many things are wrong with the way you define, right? The states like this. The first is that 1 tilde and 3 tilde have overlapping, right? Pattern has overlapping states. Because, right, I mean, when we write down star 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 like this, we mean, right, whichever, right, comes before 1 is okay. But if we say we do that, then 1, 2 we cannot distinguish, right, from whichever. So to distinguish that, we need to do something like 1, 2 complement, right? Well, I guess for the same reason, we probably want to do something like this, right? And then, right? So complement here means whatever it is, but not 1 and 2, right? For example, can be a 3 and a 1, for example, for these two previous states. So now, but even then, right, this is not enough because of state 0 here, right? No pattern. Well, so that actually will sort of becomes the second part of the point to consider. Sorry, A, right? How to define the state. And then B is how to write down the transition matrix, right? So both of these, even though we kind of write them separately, right? Because we can't really write them simultaneously. In reality, you kind of have to consider them together because you cannot just write out the state without thinking about what kind of, right, transition probability you will associate with that state. Case in point, for example, with the 0 tilde here, when we think of 0 tilde as no pattern, then when we say something like Q 0 tilde 1 tilde, right? What would that be? And we said, right, for the transition matrix of a Markov chain, the number one requirement is that probability that you will be at some state condition and you are at some other state must be completely determined, right? As a function of I and J, right? That's sort of like what it means to be a Markov chain. So if you can't really write down something like this, then your definition of the state or the way you consider the model of the Markov chain is actually not gonna function, okay, as a Markov chain. So And the reason why, right, in the pattern tracking problem, we cannot write down something like this is because no pattern here hides, right, a lot of possibilities. For example, 0 tilde hides something that ends with 3. Sorry, something that starts with 3, right? Something that starts with 0, something that starts with 2, but, right, 2 is here as well, so we need to distinguish that, but not a 1 right after, for example, right? So basically, these 3 will have different way to transition to, say, into 1 tilde, right? Because this moves to 1 tilde would be P31. This moves to 1 tilde will be P01. And this moves to 1 tilde will be P21, right? And so they cannot be combined, right, into the same state. And I mentioned last time, right, one thing that you want to keep in mind when we deal with Markov chain is that the transition probabilities, right? So basically, it's kind of obvious, but in a Markov chain, xt plus 1 and xt generally are not independent. Okay. And so what that means is, say, when you add Pij, when you add over I, okay? Meaning that you look at the column sum of the transition matrix. This most of the time has no meaning. It's not a fixed number, right? In contrast to when you sum over j of Pij, this must be 1. It has a meaning, right? So this sum right here represents the probability that you start at I, the chain starts at I, and then go to some state. Of course, right? The probability is 1. If you start at I and you go into some j, some state, that's the probability is 1. Here, right, means you start at all possible states, and then so the probability that you go into j from all possible starting points. Now, it might sound like something sensible in English, maybe, but mathematically, this makes no sense. I mean, it's not that it doesn't make sense. It's just basically you cannot give any further interpretation for this statement. The reason is they're all conditioned on different events, right? They're all conditioned on different starting point. And this is not joint, right? This is not j and xt equals to I. No, this is conditioned on xt equals to I. So effectively, you are in different universe. And if you're in different universe, the probability just cannot add because, you know, it's like apples and oranges, right? So from all those points of view, when you go back to a problem like this, for example, you can't really have a state 0 tilde like this. But you must have, you know, state 5, state 6, state 7, for example. All right. So that's sort of a second example to demonstrate, right, the kind of the labor involved when you define a state, right? A Markov chain, as far as we're concerned, the state has a lot of meaning. It can take on a lot of meaning. And how you choose to assign those meaning will decide how you solve the problem, or even decide whether or not you can apply the Markov chain theory to it. The last example, I guess I wrote down the part B here, right? But the last example from part A that I want to talk about is just basically, right, the mundane one where we try to group together some states, right, and make them absorbing. Right? So that letter, right? The reason why, right? So basically, this basically calls attention to the special meaning of an absorbing state, right? So which one do you decide to model as absorbing? The reason why absorbing state is important, right, is just from its property, right? Once you're at an absorbing state, you will not go anywhere, right, after that. So basically, an absorbing state, right, if you look at the transition probability from a state, let's say, into the absorbing class after so many times, what it really means is not that you move from I to the absorbing class in so many steps, but it includes all the scenarios before it, meaning that you may be in the absorbing class for all possibility. Sorry, this is not for all, right? Some masses. Right. Okay. So the possibility that you are at the absorbing class sometime between 0 and t, starting at I. And it all comes from, right, the class being absorbing. And why would this be important again? It's important, for example, right, in the pattern tracking problem, where we would make whatever, right, we're tracking once we there into absorbing. So, right, that's the first thing. But on its own, right, absorbing state, absorbing class can be used to handle, right, the calculation of, right, a path probability that exactly, right, happens to avoid, let's say, the absorbing class, right? Because again, right, actually from the same consideration, so I guess here, right, by definition, I cannot be in the absorbing class, because if I is in the absorbing class, this will be 1, right? You will not escape it, the absorbing class, if you're there. So the reason is because if ij are not in the absorbing class, then p to the ij, right, p to a t at ij entry comes with the free property that you are at j after t steps, you are at I, so you start at I, but you will never be in the absorbing class in between, right? This comes for free because, right, if you move from I to J and A is absorbing class, and if you're there, you stay there, right? So the fact that you made it to a state not in the absorbing class as time t means that, you know, you are not, you were not absorbed, right, along the way. Is that okay? So again, right, I would class this, you know, it depends, right? under the consideration of making some states absorbing. And when you're skilled with this, you can kind of handle certain probability calculation more easily by doing that, right? By making into something in absorbing class. So that's example 3. So these are 3 examples, right? But there could be more. But these are the highlights, which is basically about how to model a state, right? Or not how to, but when you model a state, there are a lot of considerations. So for part B, how to write down the transition matrix, right? Well, actually, part B here also has some connection with the absorbing class, right? Because, so basically, part B here has a lot to do with, you start out with a matrix P, right, of a process X. You want to move to a matrix Q of a process Y, right? As you've seen with our problems, a lot of times you may not have to start from scratch, from the English description of something, some phenomenon. You may, but sometimes you might start with a Markov chain somewhere is given. And what you do is you modify that Markov chain by relabeling, right? Relabeling the states, or group the states together, right? In some way to come up with some new process. And from there, you have to rewrite, right? The new transition matrix. And here, the process is just probability calculation. There's not much we can say about that, right? Besides the fact that, you just have to read what's going on and write down the transition matrix. Is important, okay? It cannot be skipped. I mean, when I write down a few lines of some problems and I just stop there, it means that I leave the rest for you to fill in, right? Because we have more important things to go over. It doesn't mean that you can do the same thing, right, on your homework on the exam, right? You have to write down everything, right, of the matrix, okay, to get full credit or to count it as you've done the problem completely. So that's the second consideration. The third consideration for a Markov chain, of course, is how to write down, right, CERN path probability, right? And here again, it really is about you reading the English word and try to interpret it, right, accordingly. For example, right, we could have something like probability, right? Let me just show you. For example, if you look at this, XS not in A, this is for all, right? For all. Okay. And then XS is not in A, some S. These are 2 different statements. Okay. It's really kind of, if you have taken real analysis or math 300 for that matter, this is for all versus there exists. These are 2 different quantifiers, right? And as you should have learned in math 300 or real analysis 311, they really are different, right? Here, you have to make sure it works for every S from 0 to T. Here, some S in between would be fine, right? It's an and an or, that kind of thing, right? So, well, Well, I don't know, right? You have to kind of really think about the statement. For example, if A is absorbing, then right, P to the T ij for ij not in A will right come for free, will imply right that you're at J at time T, you start I times 0, but you are not in A, right? Anywhere in between. Okay. But what if that's not what you're interested in? What you're interested in is a probability you are at J like this. Sorry. No. So, but what if you're interested in something like this? You're interested in probability that you are absorbed at time T, but you are not absorbed anywhere, anytime before that. Sorry. So this is strict. Right? What if you're interested in that? Okay. So again, why not, right? So the reason is because if you write the answer here as P to the T I A, this is incorrect, right? The reason is because right, A is absorbing, so P to T I A will have the possibility, right? So P to T I A will be the probability that you start I, you end up at A, but you end up at A for some S. Between 0 and T. All right, which is not what you're looking for here. Do we understand? So it's those subtleties, right, that you have to pay attention to. That basically, if you're looking for this statement, then this is not the answer, right? The answer is what? The answer actually will be, right? So the answer is, right, P to TIA minus P to T minus 1IA, right? Why? Because this is a probability start A, I, and absorb, right, at A, at T or before. And this is a probability start I and absorb at A at T minus 1 or before. So you subtract the two together, right? That means the probability start I, but get absorbed exactly at T, because you subtract away, right, all the probabilities that you get absorbed T minus 1 or before. We understand? And then, right, different other scenarios, you want to be at some point, along the path, then you just insert, right, the right time at the right location, just patch up the path. You can also have, something like this, but I is in set A, right? Or J is in the set A. Then you have to do the first step or last step analysis, right? That kind of thing. So for example, just write out one thing, right? Let's say xt equals to J. And then, what is it? But you want to be at J and you want to not be, right, at A less than T. You start I, but the catch is you start not in the absorbing class, but you end up, right, in the absorbing class at the. So I think, right, actually here, I kind of muddle, right, some steps here. Basically, if you look back into the lecture before, there are two processes going on, right? There's the X here, where, right, we pull the states together, we call that them absorbing class. And there's a Y here, right, that works with the absorbing class A, right? So maybe I should be clear on that. Maybe let me change all these to Y, right? No, it's fine. No, it's fine, it's fine. But what I really want to say is the matrix that we want to use here is not the matrix P, because P is the one originally associated with A, right? P doesn't have the absorbing class in it. It's Q, right? Where you pull some states together and make them absorbing. So this is Q, okay? And this is Q. We understand what I mean, right? For example, you know, if you have P to be something like 0, 1, 2, 3, right? And let's make them 0.1, 0.1, 0.1, 0.7, 0.5, 0, 0.5, 0, 0.4, 0, 0.3, 0.3, and then 0.2, 0.2, 0.2, 0.4, right? Something like that. And if you, let's say you pull 2 and 3 together, right, and make them into absorbing class, then you will have 0, 1, and then A, right, as Q, right? Where you have 0.1, 0.1, and then this is 0.8, right? You have 0.5, 0, 0.5, and then 0, 0, 1, right? Like that, okay? So P has all the original states. Q will have the absorbing class in it, right? So if we want to do some calculation that involves an absorbing class, most likely you pull out the Q calculation. But sometimes it's a mix between P and Q, for example, here, right? Where you want to calculate the probability that you start outside the absorbing class, but then you avoid absorbing class, but then you end up at some state that you consider as the absorbing class, for example, 2 and 3. Right? The problem, as we explained last time, was because Q does not see right, inside the absorbing class, right? So for example, Q does not distinguish 2 and 3. If you want something like Px10 equals to 3, and then Xs is not, right, 2 and 3, in between, and you start as, let's say, 0, right? So here, you cannot purely use the Q matrix because, right, the Q matrix won't see the state 3 at step 10, correct? So how does this work? Well, how this works, right, is that you will do the last step analysis, which also demonstrates, right, the ability that when you have a Markov chain, you can insert a point, right, in between at will using the law of total probability, right? Meaning that you consider that you move from state 0, right, to any state outside the absorbing class at step t minus 1. Sorry, Q, right? I and then K, right? So this is K not in A, not equal to A, right? The reason is because, right, by the same token, if you move from I to K, any K not in the absorbing class, then by definition, observing class, you will not be absorbed, right, in those T-1 steps. But then, right, you will move from K to J in the last step. Okay. So this right here, right, is sort of that law of total probability, or the Chapman-Kolmogorov equation, right? Modified to accommodate both P and Q. All right, so these are some, right, kind of big strokes, right, of, let's say, basic Markov chain that we can look at, that you should think about, or you should know very well, right, if you want to work with Markov chain at the basic level. Any question? All right. So the next next section is 4.3, classification of states. So let me tell you, right, what the story is. Basically, 4.3, 4.4, and possibly 4.5. Let me see. Yeah, 4.5, which is examples. So 4.3, 4.4 together, right? They're looking at something I want to call long-term behaviors. Of a Markov chain. All right. So the reason is as follows, or let me just say, right? So although 4.1 and 4.2, as short as they are in terms of the textbook, materials, they do cover a lot of materials. In other words, many questions involving Markov chain can be answered with the techniques of 4.1, 4.2. If you master them very well, there are like tons of questions you can answer. But notice that all those questions, right, fall under the category of, let's just say, finite horizon calculation. What do I mean by this? Well, notice that all questions has an end time, right? Except 10, except 100, if you will, the pattern, right? Even, yeah, let's say, where was it? The first time you see some pattern, right? Still, you ask, okay, do I see that pattern at the 10 steps? Do I see that pattern at the 100 steps? And you make, right, the time you see the pattern, you make the pattern state an absorbing state, then you're just asking whether or not I'm going to be absorbed at step 10, whether or not the Markov chain will be absorbed at state 100. The point is, it's finite horizon, right? You never go beyond a certain time. However, in this literature, or in stochastic process in general, right, there's this idea of long-term behavior, meaning that you just let the Markov chain run for a long time. And you wonder how the behavior look, let's say, on average along the path. Okay. It's a little bit vague statement, but let me tell you, right? So you let things run for a long time, and you look at the whole path together. Now it's like a long sample, right? And this actually is in the realm of something like law of large number and central limit theorem. You're not going to be wrong if you think of it that way. The only thing that's kind of a little bit wrong about thinking in these terms is that law of large number and central limit theorem deals with IID sequence, meaning that independent random variables. While what we have in the picture here, right, is a sample of a Markov chain, a time series, if you will, meaning that things can depend on the immediate previous step, right? But as I explained last time, IID sequence is actually a special case of a Markov chain, right? It's the white noise. It has no dependence on a previous step, but still no dependence can be viewed as depending on the immediate previous step. So anyway, right? If you look at the long term, so basically like you collect, let's say, stock data, right, over 20 years, you could maybe ask a simple question: the proportion of days where the stock goes up, does the stock go up 50% of the days, or more than that, less than that, right? So the long-term proportion that, let's say, the Markov chain occupies a certain states. Does it make sense? Meaning, and this is a time question, right? Over the long term, how often do you visit a certain state as measured by the proportion, right, over the long sample? That's one thing, right? So long-term average. A second question you can ask is that after a long time like this, does the Markov chain settle into some stable behavior? And this is actually a different question. Meaning this, well, we didn't do any kind of concrete calculation, but you could, right, at least feel intuitively that, right, with a Markov chain, right, we mentioned that x0, x1, x2, x3, etc. These are random variables, right? As random variables, they have distribution. But the distribution of x0, x1, x2, etc., you can bet are not same, right? They change. Okay, again, unless you have an IID sequence to begin with, then the point is, there's no point. But with a Markov chain, basically the distribution gets updated, right? Again, think of the stock. The behavior, the distribution of a stock today should not be exactly the same as the distribution of a stock yesterday. Or stock maybe is not, let's say stock, right? But in the long run, does that change? Meaning that after 20 years, can we say with some confidence, or can we say with all confidence, that the distribution does not get updated anymore? Things settle down to a pattern. I think stock maybe not be a good example, but let's say there's a problem you'll see. It's called the hotel problem, but it's a different kind of hotel. Basically, you think, right, if you open up a new business, right, then the flux of customers on the first few months, right, will be, I don't know, quite volatile, right? Some days you have a lot of customers, and some days you may not have enough customers. Who knows? But in some sense, if your business survives, then it might settle into a stable pattern, meaning that so the number of customers coming into your store will still be a random variable, meaning each day is random, but the distribution day after day will not change, will be stable. So there's that. Okay. And of course, it's not true that all Markov chain will settle into a stable behavior, but a lot do, and we want to talk about, right, which condition that allows them to settle into a stable pattern, stable behavior. And of course, right, the question of the long-term proportion, how do we calculate the long-term proportion, right? So first question, long-term proportion. Second question, stable long-term behavior. All right. And I want you to at least, I mean, if you don't follow all this very precisely, that's fine because, right, we're not doing anything concrete right now. But one thing you want to pay attention to is these are two different objects. One is an average over time, and one is like an average over space, because we're talking about the distribution over the states, right? And they're different questions. Even though, let's say a magical property always props up that these two guys actually one and the same thing. And they're connected via something called ergodicity. Ergodic theory is like a big branch of mathematics, right, in itself. So we're not going to do ergodic theory in any sense here, but ergodic theory studies exactly this behavior, the long-term proportion, a long-term time behavior matches somehow with the stable spatial behavior that the process settles into, okay? But these are the two questions that we will kind of take up in 4.3 and 4.4. And you see that in this sense, right, they're in contrast with 4.1, 4.2, because they're really, right, about long-term behavior. So they're really, you know, for lack of better words, infinite horizon, right? Meaning that you have no finite time. You have to keep pushing and pushing and take literally limit as t goes to infinity of, right, the behavior, the Markov chain. So that's the flavor, okay? But the tools that gets developed to talk about this somehow take some kind of detour about, well, not detour, you'll see, right? It talks about the number of visits to a certain state over the long run, etc. And the natural reason, right, is because these are the questions we will be discussing. All right, so let's see here. So we'll start with a bunch of concepts and definitions and blah, 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 right? And we'll see how they're connected together. All right. So some definition to start. The first definition is state J is accessible from state I, and the symbol is I goes to J, right? I is connected to J like that. But it's a directional statement, right? J is accessible from I doesn't mean that I is accessible from J, right? But anyway, this is if P to Tij is positive for some T. Okay. So pretty simple, right? What it means is that there is a path, right? In English, it means there is a path of length T, right? Because P to T and positive probability that connects I and J. And here, notice or whatever that the language starts to get a bit close to graph theory, because you are really talking about the connection between nodes, okay, via edge. So basically, you know, again, we're not doing graph theory here either, but you can imagine something like, you know, two nodes, right? Two states are connected. I mean, well, so here's a one-step movement if they have a positive weight connecting them, right? So this is Pij, right? Pij is 0.8, for example. But for example, state I and state Z, right, is not directly connected, but somehow J is connected to K with 0.5 and K is connected to Z with 0.01. I mean, I'm just making it real small. You can still have a positive probability, right, to go from I to Z in 4 steps, right? That's a path among maybe some other paths, who knows, but as long as there's one path with positive probability connecting I to J, yeah, I to J here, right? And then we say that, right, J is accessible from I, okay? So give me a moment. All right. So the next thing then is, if we have this directional statement, then we can also combine them together, right? I and J communicates, I guess, plural, if you can go from to J from I, and you can go from I to J, from to I from J. All right. But mind you that, right, here, the T, right, that gets defined, meaning, right, that there exists T S N T integers, right, bigger than equal to 1, such that P to the Sij and P to Tji is positive, right? So what we want to highlight is the fact that you don't have to go from I to J and go from J to I in the same number of steps, right? They could be different. But as long as there's a path from I to J and there's a path from J to I, they communicate, right? All right. So the notation is I communicates with J, right? Like that. And so let's do some observation. So basically, this right here, right, defines, communication defines a relation between two states, right? And this relation has some property. So first of all, a state communicates with itself. Hold on. So for this, I think I need to modify my definition. So here, right, it might sound a little bit funny, but I will need to use 0, not 1. Okay, so 0. All right, let me explain. It's a technical thing, but naturally, right, you need to take at least one step to go from I to J, right? That's why I write b equal to 1. But it's just, you really want to say a state communicates with itself, or a state is accessible from itself. You know, it makes sense English-wise, right? Because if you should be able to access I from I by not going anywhere. So just for that special case, we allow for t equal to 0. But, you know, naturally speaking, right, if you don't consider from I go to I, like immediately, then it should take at least one step. Anyway, right? So this right here is from allowing, right, for t equal to 0. Because if you say that, then it's unclear if a state I communicates with state I. Is that okay? But here, this is obvious by allowing step 0. And then 2 is symmetric, which is kind of whatever, right? It's obvious. So 1 and 2 are obvious. The third is it's transitive. And I think maybe this one requires some proof. 1 and 2, right, are obvious. 3 requires some proof. You know what? I think we haven't done a quiz today, right? So proof it. And by the way, right? A lot of questions of this chapter 3 and 4, until we go to 4, will be of the nature of proving stuff. Okay. I think proof is not, generally speaking, a student's most favorite thing, but nature of 4.3 is that a lot of proofs will be required. All right. So how do we prove transitivity of communication between two states? Well, what do we need? We need to show that there's some positive, right, number that allows you to go from I to K. Well, what is that number? Well, starting from hypothesis, right, you know that there exists S, P to the Sij, right, is positive. So, and then there exists T, right, you're going to go 0. P to a Tjk is positive, right? And then, of course, P to the S plus T, I to K, right? And in English, it's very clear, right? You can go from I to J in S steps, and you can go from J to K in T steps. So you should be able to go from I to K in S plus T steps. But if you want to be rigorous, but right, it's the Chapman-Kolmogorov, right, equation. Right, like that. But you sum over all L, right, in the state space. Of course, it includes J. Right. So this shows that K is accessible from I. But a similar proof, right? Because you do have communication in the other way. So that's a proof. Any question? All right. So that's really it, right? But what do these three properties imply? Now, in Math 300, you probably should have, or you definitely should have, learned about something called equivalence classes, right? So, hold on. I should call it equivalence relation, which will lead to equivalence classes. Right. So what are they? I mean, an equivalence relation is exactly any relation that satisfies these three properties, right? Identity, symmetry, transitivity, right? And well, what's the easiest equivalence relation you can think of? Well, the easiest one you can think of is mod, right? So, for example, let's say A equals to B mod P is an equivalence relation, right? Because A is equal to A equals to B, you know, that kind of thing, right? And the most important thing about equivalence relation is that it breaks the universe where you're looking at into equivalent classes, right? For example, in the mod P relation, it breaks the integers into equivalence class. Which ones? Well, the ones that we don't even bother to think about, right? When we say 0 mod P, we really are thinking of what? 0, P, 2P, 3P, etc., right? I mean, in negative numbers. All of these are equivalent, right, to 0 mod P. Yes, and so that's it, right? So basically, equivalence relation always break the universe down into equivalence classes. And so here, by communication, we have an equivalence relation. So this relation breaks the state space or partition the state space, can be partitioned into equivalence classes using this. All right. I forgot in graph theory what they're called, but the intuition is pretty simple. Basically, if you have a bunch of arrows, and if you chase them, right, and they form a closed loop, and you know, they don't go out of themselves, then this will form a class, right? And you can also take out another one, let's say 4, 5, and 6, for example. And of course, the picture is oversimplified here, but right, basically, again, right, the arrow here represents a positive probability, right, to go from I to J in one step. But for example, if you chase the arrows, right, and then you have this, then basically there are two communicating classes, right? So sorry, let me call this communicating classes. Okay. Within this space. So maybe let's look at the example, right? P equals, so 0, 1, 2, 3, 4. like that, right? So this is a transition matrix, right? So here's a quiz for you. Write down all communicating classes of P. Okay. So how many classes? How many communicating classes does P have? Should have 3, right? So 0, 1 just communicate among themselves. 2 and 3 also communicate among themselves, right? Again, this picture right here is not necessary. I'm just kind of drawing it out. Now, state 4, right, seems a bit funny because it goes into state 0, goes into state 1, and it communicates with itself, right? But you see that from the definition of communication, state 4 does not communicate with state 0 and state 1, right? Because there's no way you can go from state 0 to 1 and to 4. So 4 does not communicate with 0 and 1. In fact, right, the only state that 4 communicates with is itself. So, right, there are 3 communicating classes. Okay, so far. But of course, right, the nature of 4 is very different from nature of 2, 3, or 0, 1. We'll talk about that later. Any question? Now, to connect this to something we've seen before as well, I think, right, question number 13 from the exercises, right, but it will be your homework soon. It says that if P is a transition matrix, and if P to the R has all positive entries, then P to the N also has all positive entries for any N starting from R, right? So we did this question last time, but from the point of view of the Chapman-Kolmogorov equation, just how to prove this. But now you can see, right, besides proving it, there's the whole interpretation, right? That's very interesting from this question. First of all, right, it says that whatever this Markov chain is, it has only one communicating class. Because after R steps, you can go from any state to any state, right? So it has only one communicating class. But it also says something along the line that, right, if there's like a lower bound, right? There's number such that any state can communicate with any state within that number, then you're guaranteed to be able to travel, right? So if that the sort of like it's not doesn't have to be the shortest path, but let's say the shortest path, right, to go from any state to any state is R, then you guarantee that you can go from any state to any state using more steps than that. Okay. So that's kind of interesting if you think of it, because like I explained, right? If you can go from I to J in 10 steps, why is it possible to go from I to J in 11 steps? Because, you know, at least superficially, you think of it, if you search, it might not be possible, right, to add one extra step in and then still somehow to go from I to J. You know what I'm trying to say? At least it doesn't seem immediate to me that that's possible until you look at the structure of the chain itself. But in the abstract, you can. You can always insert one more step somehow. Of course, actually, I should backtrack, right? That it's not. It probably is not inserting one more step, meaning that the steps that take 11, the path that takes 11 steps may not have much to do with the path that has 10 steps, or may not just about inserting one step. But still, right? The assertion is that if you can make it in 10 steps, then you will be able to make it in any step beyond that. Of course, the requirement is that everything has to be positive. Right? It's not just for a particular path. That's not true. If you can go from I to J in 10 steps for just some I and J, that doesn't mean that you will be able to go to from I to J in 11 steps, right? Again, demonstrating the subtlety of like quantifiers and things like that, right? This is for all. Okay. Any question? All right. So let's, since we have that, right? Let's give a name as well. A Markov, so definition. A Markov chain that has only one communicating class is called irreducible. So irreducible is the name, right? It's a technical word. It means the Markov chain only has one communicating class. And so you wonder why, or what's the meaning here? Well, besides the obvious meaning, you can also note something like this. A communicating class in some intuitive way, right? It's like a mini Markov chain in of itself. I mean, of course, besides this one, right? This one sort of like will intuitively you see that you will not stay there for long, right? Eventually you will get absorbed into one of these communicating classes. But for those stable one, or the name really is recurrent classes, right? We'll talk about that soon. Then they behave like a mini Markov chain in of itself, right? In of themselves. That means that they're really right one, two Markov chains really with sub Markov chains right inside the big ones. And that's sort of like you can reduce the big Markov chain into so many small Markov chains, right? That operate independently, not independently, but operate separately, right? With among each other, depending where you end up. But so that's where the term reducible or irreducible comes in, right? But if it's irreducible, that means the Markov chain is every state. So you have to look at all states together. You cannot reduce it to a smaller one, right? By somehow zooming in into right? Where not. Okay. All right. Now, more technical definition. This one will be a term. So for any state I, define f sub I. This is the name. Is probability that you start at I, and then you return at I for some t. But of course, this time, right, it's at least takes one step. Okay. So first of all, let's explain this, right? This is a, let's say, infinite horizon definition, because, you know, you have no limit on what t can be. But this is not that one above where we allow for, well, you're already at I, so there you go, right? No, you have to take at least one step out. So it's really about, after you have ventured out of state I, will you ever return, right? So this is, if you want English word for it, this is probability of the chain. Let me throw in the word ever, right? Returns to I, condition on starting it. And when you look at this, right, you see that, well, it may or may not be guaranteed. By the way, right, there's another way to state this, which is, I don't think we'll have to use that, but that way, but let me just mention for now. It has to do with the first visit time as well. If you define first visit time, right, maybe, let me mention it too. Let's say tau I, if you define it as the first time, such that you return to I, start at I, right? This is a stopping time, remember, right? That we talked about. So basically, sorry, first time bigger than one, right? Then Fi basically is probability that tau I is finite. Okay? Because if you return to state I after so many finite steps, then you do return to I. But here's a random variable, tau I, that can take on an infinite value, right? I think you might have learned in real analysis that the infimum of an empty set is infinite, right? Well, you see that it's kind of consistent with infimum, but let's not go in there. But let's solve this way, right? If you never have a minimum, if this is not true, then the minimum is infinite, right? And so, like that. Anyway, right? So the point, right, as you see, is this guy is, of course, it's a positive probability, but it's either less than one or is equal to one, right? There are only two possibilities. Well, can it be zero? Yes, of course, right? But zero is built in, right? Sorry, built in here. Okay. So anyway, but let's take a look, right? For example, with these two states that we looked at, then clearly, right, the probability of returning to zero, starting at zero, is one. Probably returning to one, starting at one is one, because you will, right, never escape this combination of zero and one. And you can see that you can just not keep going to zero, right, for forever. Eventually, you will have to go back to one, right? But the probability that you will revisit for is not zero, right? Because you can only revisit 4 if you keep returning like this. And it's not 1. It's not guaranteed, right? Eventually, you will not return to 4. Okay. So these are the two possibilities as demonstrated here. Any question? And so, right, we have the name according to this. If fi is less than 1, we call I transient. And if fi is equal to 1, we call I recurrent. So this is yet another definition, right? A state is transient if fi is less than 1, if the chance that if you're not guaranteed to revisit the state starting at the state, but if you're guaranteed to revisit, then it's recurrent. Okay, any question? So in this sense, right, you can prove, or I'll say later, but prove, right? So one question here is prove that 4 is transient, and prove that 2 and 3 are, and 1 and 2, 0 and 1 are recurrent. Okay. So then let's move to the next definition, which is about the number of visits. To state I, starting at I. All right. So several things here. So first, just let you give something a name. Let's call n sub I. Okay, is this. You know what? Maybe let me state a definition. Let I sub n, the indicator, to be 1 if xn is equal to I, 0 if xn is not equal to I. So this is an indicator function, right, that we've seen in previous chapter, that basically track whether at time n, at time n, you are at state I or not. Okay. Now, if you sum up all these guys from 1, you know what? Actually, from 0. The definition is from 0 to infer the condition on x0 equals to I. This will be the number of visits to state I, starting at I. Okay. And again, notice, right? It's just like the little annoying thing that is the theme of these definitions. Start from 0. That means that the number of visits is at least 1. Because you're guaranteed, right, to visit it at least 1 when you condition. Are we okay with this? It's just how it's defined. But clearly, right, what we're interested in is not about is being 1. But what we're interested in is whether this is infinite or is it finite? All right. And you can bet that is connected to the probability of revisiting less than 1 or equal to 1. The probability of returning or revisiting, right? The reason is as follow, right? And let's again, right, take 4, right, as an example. The number of returns or the number of revisits, right, to state I. So you can call this revisits, if you will, right? To state 4, starting at 4, you can see that, right, it's guaranteed to be finite. It cannot be infinite, because the probability that you revisit for infinitely many times will be 0, right? Because each time is 1/2. 1/2 raised to infinite will be 0, right? So on the other hand, the number of visits to state 1, starting at 1, should be infinite, okay? The reasons as followed. So first of all, right, let us qualify the statement. The probability is really talking about probability ni equals to infinite equals to 1 or not. Okay, that's the question. And so let's explain. So basically, right, if you are at a recurrent state, if you know that your Fi is equal to 1, right, and you can prove it, but if you know that you're guaranteed to return to a state, then first of all, right, the probability you try to return to this state is 1. But after you return there, then you're again guaranteed to return back one more time. And then you're guaranteed to return back one more time, etc., etc. So, right, normally speaking, right, for example here, when you return to a state like this, it costs you something, right? It costs you 50% chance to return. And then, of course, the next time it will cost you 50% chance. So 50% times 50% is 25%, right? By multiplication. But if it's always 1, 1, 1, 1, then if you keep multiplying, it's always 1, right? So that's why it will never diminish. So therefore, that's why the probability of visiting infinitely often is 1, right? Or what we're saying is this, right? The claim is that if state I is recurrent, that is, if Fi is equal to 1, then probability of ni equals to infinite. Okay. Now, the proof of this is we just did, but I just want to mention that here it requires something called strong Markov property, like this, right? Basically, the point is the following, right? Normally speaking, when you say x0 equals to I, and let's say x10 equals to j, and you look at x11, x12, etc., right? Then basically, you say that, well, x10 is j, so I can forget everything before that, right? That's Markov property. On the other hand, right, you say x0 equals to I, then after so many times I don't know what, in fact, right, it's a random time, and you return to I. And then you look at times beyond that. You see? And you say that, well, once I return to I, then I can forget anything before that, right? The past history doesn't matter. It's as if I restarted I, right? This is not, technically speaking, it's not Markov property, because you don't restart at a finite time, or you don't restart at a concrete time, at a deterministic time. You restart at some random time. You restart at some time when you return to I. But it still works, meaning that the Markov property still works. You just, for all intent and purposes, think that you start at state I. You can reset this to 0 and count forward 1, 2, 3. But in order for that to happen, is something called a strong Markov property. And in some advanced courses, you will need to prove that the process has the strong Markov property. Okay. Here we take it for granted that whatever we're discussing does have strong Markov property, but it's what's used here, because right after you can conclude that the chain, the process reset when we return to state I, right? Then basically this is Fi, and then some other time. So this is another tau I, right? This is another Fi. Okay, and they're all ones. So therefore, basically something like probability Ni plus 1 equals to Ni is equal to 1. Because, you can always take one more step, but only, right, infinite can do that. Does that make sense? All right. So basically, right, it's, let's say, pre-intuitive that, so to recap, right, if a state is recurrent, and you have to know it somehow, right? But if you know it, meaning right now, the only way you can know it is by establishing somehow that Fi is equal to 1. Then the number of revisits to that state is infinite. All right, starting at state. Okay. Now, what we want to do next is, what if a state is recurrent? Sorry, if a state is transient. How does Ni behave? How does the number of revisits to the state starting at time I behave? And here, right, you see that, sorry, give me one moment. I need to recharge my laptop. And here you see that Ni behaves like a geometric random variable. With success probability Fi. Sorry. No. 1 second. Ni is the number of visits, right? I think success is 1 minus Fi actually. Okay, let me explain. So what is success here, right, to begin with? So, and what does Ni count? Ni count the number of visits, right? Until what? Until you never return. So the never return is in the geometric language a success, right? Because geometric counts the number of trials until the first success, right? So basically that's why 1 minus Fi is the geometric random variable. Okay, so let's check if this is true, right? So for example, you are right, and let's take the state 4 here, right, as an example, right? It says that, right, so state 4, right, you are guaranteed that you visit once, right, because you have state 4. What's the probability that you will visit twice? Or the probability you visit twice will be, sorry, hold on. Now that let me say, sorry, I said wrong. Right, so the state 4 here, right, has this 1/2 here, and then 1/4 to somewhere, right, and 1/4 somewhere else. Okay, like that, right? That's state 4. So what's the probability that N4 equals to 1? Well, you start at state 4, right? So you will visit once by definition, but you will visit only one time if you don't return, right? If after the first chance you don't return, so that's 1/2. If you start there, right, then you move away right away. Does that make sense? That's 1/2. And probability that N4 equals to 2 is what? Well, you know what? The 1/2 here is unfortunate because it does not distinguish, right, between 1/2 and 1 minus 1/2. So let me modify this. Let me say this is 1/3, and whatever these are, right, to make them into 2/3. So let's say that. Okay. So probably N equals to 1 is actually 2/3, right? Because you will move away after one step, or probably 2/3. What about 2? So you stay there, right? It counts as 1, but then you have to revisit once, and then you will move away. Agree? And then if you look at 3, same thing. You have 1 visit at the starting point, and then, right, you have to revisit 2 more times. Oh, right, so that's 1/3 squared, and last one you have to move away. All right, but so this is the taking that Markov chain, right, and make it concrete. But you see, right, using the strong Markov property, meaning that after you return to a state like the chain refresh, we can update this picture into this. This is state 4, but this is not 1/3, but this is Fi. Right, so needless to say, right, Fi is a random path. It takes a long time for that to happen. But basically, the big picture is that's Fi, 1 minus Fi, right? I don't care how long it takes, but there's a probability that you will return here, right? And that counts all possible paths for you to return. maybe for state 4 here, there's an immediate path to return, but there's also another long path to return. Then the Fi will add both of these together. But anyway, so, but you see, but if you replace 1/3 with Fi and this is 1 minus Fi, nothing will change. In other words, right, probability that Ni equals to K will be 1/3 raised to K minus 1 at Fi, and then times 1 minus Fi. Right, K minus 1 is because you have the first visit for free, right? Okay, so this is exactly a geometric random variable. And you see, right, in this sense, if F, and we're talking about, right, Fi less than 1. Less than 1, you have a geometric, keep on having failures, right? That thing right there. Sorry, somehow I think my screen sharing is frozen, right? Okay, right, that thing right there. Okay, but so here Fi is less than 1, and so you see that probability that Ni is finite is 1. You will revisit guaranteed finitely many times. And in fact, right, the expectation of number of visits will be 1 over 1 minus F. Of course, right, if I is recurrent, so this is I transient. If I is recurrent, then expectation of Ni is infinite. I mean, more strongly, right, probably Ni equals to infinite equals to 1. Any questions so far? All right. So now, so far, those are definitions. But I think I did raise a question of how do we know if a state is recurrent or transient? And right now, the only thing you can do is by definition, right? By definition that you have to check that Fi is equal to 1, or Fi is less than 1, right? So but the point is this. This is actually not easy at all. Why? Because to check Fi, you have to track all possible paths that go from I, that start from I and go back to I. All right. So let's say not simple, because you need to track all paths of all possible lengths and goes from I to I. And you have to calculate the probability of all those paths and add them up. Okay. And so this is why we need a different result that somehow makes it easy, because the combinatorics of this is simply not tolerable. So B here is by the following result. So I'm just trying to explain why the next result is kind of relevant. And it starts with, right, a clever way to look at the definition of the expectation of Ni. If you look at expectation of Ni, right, remember Ni is the sum of these guys, right? So the sum of the, you see, this is what now start to come back on why indicator function is important. The indicator function counts at each time step whether or not the Markov chain visits state I. So this will be this expectation of the sum of In 0 to infinity condition on x0 equals to I. But now you can move the expectation inside and it becomes a probability because it's an indicator function. Probability that you are at I condition on, but this is nothing but p raised to the n I, the transition matrix. So once again, right, this may not be the easiest thing in the world, who knows, because it requires you to raise the transition matrix to all possible power and looking at the II entry. But at least analytically, you have something to do versus listing all possible paths, which is a combinatorics thing that we don't have a concrete expression for. All right. Here you have a concrete expression. Whether computationally it's doable or not is different. It's a different question. But at least you have something to do. Raise the transition matrix to all kinds of powers and look at the II entry, right? And of course, right, this is equal to infinite if I is recurrent, and is finite if I is transient. And even more interesting, right? More interestingly, in a finite case, you even know what that is. It's actually equal to 1 over 1 minus Fi. So in other words, right? Well, of course, here you know Fi equals to 1. And if it's just finite, you can also figure out what Fi is by doing 1 divided by this sum. So if you can calculate this sum, you can calculate Fi. So basically, Fi is equivalent to knowing this sum. And this sum, right, again, the reason why it's important, at least in theory, is because it deals directly with the information we're given, which is the transition matrix. Any question? All right. So now let's look at one last result for today. Which is that recurrent and transients are communicating classes property as follow. What it means like this. If I is recurrent and I communicates with J, then J is recurrent. If I is transient I communicates with J, and J is transient. Okay. And so in that sense, right, you see in this Markov chain example, that if we can establish somehow that one is recurrent, then automatically zero is recurrent because zero communicates with one. And same thing here, if two can establish that two is recurrent, then 2 and 3 automatically are recurrent. And okay, because 2 communicates with 3. Right. And maybe, just maybe, right, that raising this matrix to any kind of power may be easy by using block multiplication, but we'll leave that aside. So before we prove this result, right, which is the last thing we'll do today, this will be the cap of midterm 2, which is going to be on your next Friday, right? Same thing as midterm 1, in class via responders, etc. So midterm 2 materials. So it's not cumulative, but in some way it is, because materials from chapter 1 and 2 are still relevant. But the questions you will be asked for the midterm will focus on chapter 3 materials, and in terms of chapter 4, 4.1, 4.2, and 4.3, you should have seen, right, the questions on 4.1, 4.2 in your homework-ish. I mean, here, right, there's some questions regarding path probabilities that we just did in the lecture, right? Not sure the homework has them. 4.3, you'll see some homework, assigned, right, after today's lecture. Okay, so these are the materials for midterm 2. All right, so now let's prove this, right? So how do we prove this kind of statements? Well, we're not going to prove this by showing somehow that fj is equal to 1, for example, if fi is equal to 1. Because again, right, if you know that you are guaranteed to revisit I, and I communicates with j, well, maybe you can do it. It's just, I don't know, right? It's basically, if I communicates with j, meaning you have a positive probability to go from I to j and j to I, and you're guaranteed to return from I starting at I. Why does it make sense that you're guaranteed to return from j starting at j, right? So that kind of thing. Again, you can work it out, but let's do an easier one, which is this. As you see, this is an easier tool to manipulate than the other argument using fi, fj. So what you want to look at is the sum p to the n, but now jj. And we want to check whether it's infinite or not, on the assumption that p to nii is infinite. Right. So how would this work? Well, p to the n jj, right? Well, you know that I communicates with j. So p to n jj for n large enough can be broken down into p to the n ji using some step, p to the ii using some step, and then p to the I go back to j using some step. For s plus k plus t is equal to n. All right. St here is fixed. meaning that right, since I communicates with J, there is S and T such that this is positive and this is positive. Sorry, GI. Okay. So what that means, right, is that, so here, for example, if N is quite small, like 1 and 2, you may not be able to squeeze enough steps in between to guarantee that you can go from J to I first, and then go from I to I in K steps, blah, blah, right? Because it takes some time to go from J to I and then I back to J. But doesn't matter because, right, if you look at the sum, let's say from some large enough N to infinity of P to N J J is equal to infinite, then this sum can only be larger because this sum, it has more terms. So what I'm saying is like, it's without loss that you can consider for some N large here. Because if this is infinite, then this is also infinite. But if N is large here, then you can squeeze in, right, S and T to make it happen, right? So for N large enough, let's say, and exactly how large? Bigger than S plus T. Because again, right, we just need to be able to squeeze in S and T here. Then sum, right, let's say S plus T to infinity, JJ will be the sum. Sorry, let's say K, right? Sorry, no. How to say this? It will be bigger than or equal to K from 0, P to S J I, P to K I I, P to T I J. All right. What's the reason? The reason is pretty simple, right? To go from J to J in N steps is, at least go from J to I in S steps, go I to I in K steps, and then go back from I to J in T steps. So here, right, N starting from S plus T. So that's why, right, S plus T, and then plus 0, right? Or, 1, 2, 3, etc. So here, right, we're thinking of S plus K plus T exactly as N. But of course, right, these are things that don't depend on K, so it can be factored out. And this is good enough, right? Because this one right here is infinite because I is recurrent. And then these two are positive, so it cannot make that into 0. So this is infinite. Now, if something is bigger than infinity, that mustn't be infinity. So therefore, this is infinite, and therefore, this is infinite. Any question? Now, you can prove a similar statement for, a finite case, right? But in fact, you don't even need to, because notice, right, communication is symmetric. So I recurrent, then J is recurrent, and J is recurrent, and I is recurrent as long as they communicate. So therefore, right, the contrapositive of this statement is if J is transient and they communicate, then I must be transient, which is this. So you just, take the contrapositive of this statement and you get this. Logically, you don't even have to go through a proof. But if you want a challenge, right, to write down the statement, you can reprove this and show somehow if this is finite, then this must be finite, right? Using the split of the path. Well, you can just use logic to prove it. All right, any question? All right, so if not, then we'll continue with this next Monday.